this world becomes now you immediately see why I do this. I just actually rotate my coordinates so artificially, right? So what I do actually, if I do, I have this one. This is my y. This is my zx and yx, and simply this is y bar. This is z bar. You see here, if I simply replace H23 by H22, I get the same result, right? But not in terms of y bar and z bar. Which means, for example, if I want t equal t naught, if I H2, the positive, then these guys will stress, right? So if I'm going to consider a circle like this. So before the gravitational pass this circle, but once it passes, let's say, t equals 0 pass now the gravitational wave, positive this actually stress here. Right? So but squeeze here, stress here along this direction because this guy is positive. So this section. Then you can see I will get something like, right? So later, for example, this guy becomes negative, then this will be a stress. This will be a squeeze. But in any case, you can see the x, the long x is always either along x bar, y bar, or z bar, which means 45 degrees. Remember, h bar, H22 is either along y or z, but here is along the x is 45 degrees. So that's why we say this is called cross parallel. This is the exact cross, 45 degrees. So we have cross parallel this is 45 degrees. Einstein electromagnetic waves is also transversal, but it's 90 degrees. One is in y direction, another z direction. Gravitational wave is 45 degrees. Okay? So how you can see more clearly 45 degrees when we come back to see the geodesic waves, there you will see clearly this is 45 degrees because you need to make rotation. Okay? Yeah. So, but this actually normally in a textbook we interpret the paradigm this way. Like what I have been emphasized, really definitely use geodesic waves because you are very consider the geodesic waves two arms. The distance between test particle. The arm is H actual point is considered by test particle, right? So the two arms will not affect the gravitational waves we measure, right? The two arms also produce gravitational field. But this
L-shaped. Why it is L-shaped?
L-shaped is like what I said. You can actually easily actually this is the interferometer max 45 degrees. Yeah. So you can actually, that's a good question. The next generation of them, the US is proposing, it's called aeroship. Aeroship, this actually is 40 kilometers, this is 20 kilometers. But the current is 4 kilometers, 4 kilometers, it's a circle. The naked one, because the accuracy is hard. This is technical. I just want to see this is what to do. Why technical, I have no idea. So the naked generation is still 90 degrees, but the two arms will be different. So this is 40, is 20. This accuracy, this increase the accuracy. I do not know technical. experimental. This is actually called cosmic explorer. This is still actually not pure thinking, has not been supported yet. This is the US idea. In Europe, they also propose this actually they use underground. This is a triangle. It's a see, you can see each of them like arms. Now it's not actually 90 degrees, it's 60 degrees. So this is actually the European, this is called Einstein telescope. So this is ground, basically. These are painted all the triangle in the space. Why space is good? Because this actually this actually 2.5 million kilometers. So this is very long. Very long. This is actually over zero. The gravitational waves were more wavelength. You know, when we measure this, gravitational waves are roughly equal in order of the arms, right? The arms were over zero. So these are over zero, actually large gravitational, long gravitational waves. For example, if you have two supermassive black holes, they produce gravitational waves. That gravitational waves exactly in the least bound. So to observe gravitational waves exactly like an electromagnetic wave, you need to have two conditions. First, the signal is strong enough. Second, has to be in your observation band. If the signal is very high, but the frequency is very high, we cannot observe, like our ears. No matter how strong signal, if it's out of the band, we can hear it. Twice is not. The same thing for detection. Two conditions, signal strong enough. Second, the frequency is same amount. So these are actually, in China there are two actually also projects. One is called Taiji, another Tianqi. Tianqi is actually, this actually leads actually with our sun as the center. It's called Earth orbit. So this is actually stable orbit. So Taiji is the Chinese, is actually about 3 million kilometers, larger than this one, but the orientation is perhaps a little bit different from LISA. They want to actually to test the difference, like what I said, like India and Lago, so they want to observe the polar distance. Tianqi is actually the center of Earth. So there are some actually arguments because center of Earth, the noise is too big. Tianqi seems they got a lot of money. The first phase they got actually, if I remember correctly, about 1 billion yuan. 1 billion yuan. So, yeah, 1 billion yuan, all in Tianqi. There was actually a project 3 years ago from a Chinese technology ministry. They investigated actually 1 billion yuan for both Taiji and Tianqi. So they are still in the phase study, like these are the much advanced. These actually already have the first pathfinders in 2017 is better than what I expected. So US actually not said, okay, that's too costly. At the very beginning, they called LISA, then US will withdraw from project. European got angry, so okay, we're going to change the name. LISA became aegis. E means European. So after the 2017, NASA, the US said, okay, that's very good. We want to join again. So now, actually, again, NASA and the European join together. They come back with a LISA. They get rid of E. So I hope this will last. So there are competition between US, Europe, and also China. China actually want to build two. So I think it's not a two. Finally, will be one. But this anchor is the next generation, the space and the ground basis. Also, Japan, so they have very high techniques. So we have LIGO, we have worked with the European. We also have anchor called GE 600. GE is the first generation, German and England. So,
Japan also has Tama.
yeah, German Dama is 200. Was you there in 1990?
No, I was in GIAN meeting in.
Oh, you were there?
Yeah.
Okay. So I was actually in Tama, actually. They had a meeting. So in 1999, it's the first time I went to Japan. So I was told a story. So they saw, because they tried to, they're small, this is 200 meters. US is 400 meters. So they built quickly, they want to first detect Earth wave to get a Nobel Prize. But I think that's very clever idea. So unfortunately, 200 meters, the sensitivity is not good enough. When I was there, this sort of parameter definitely is not a Gaussian wave. Because they find the signals so strong, it was crossing their head. They said, where does the signal come from? Even some people, the car passes through actually make a noise, but this totally did not come. You know what's happened? They finally said, okay, there's a work actually about 2 meters wire. Oh, do we have one now? Okay.
Yeah, we can break now.
Okay, yeah.
I just want to add one thing.
Uh-huh.
The first LIGO meeting, the first meeting of LIGO, when they were planning for LIGO,
Yeah.
was organized by me and Sanjay Jingan at Jamia,
Oh, okay.
from Indian.
Okay, I
And
see.
all over scientists came from all over world. First
Uh-huh.
time it was in India International Center,
Uh-huh.
and 3 days conference,
Okay.
and 2 days were in Jamia.
Oh, okay.
And myself, Jingan and Bala here,
Okay, I see. Yeah.
we organized that meeting. Although,
That's perfect.
yeah, it was only supporting, we were only supporting.
Uh-huh.
Supporting. The main people came all over, we provided our facilities.
Yeah.
It started here.
Okay, good. Yeah. 00, 01, 02. Then see, if I purposely choose this guy, I will kill other folk. Okay? So this is logic. Yeah.
So that by properly choosing the zeta functions, we kill off the other terms.
Yeah.
So is that, how do we know that choice is unique?
Sorry?
That choice is unique, how do we know?
That choice is not unique, but the degree is unique. Right? So you can, for example, you can choose Q, let's say, I'm going to choose Q H00, H01 all the cluster. Only leave H22, H23. You can choose others. But the physics does not change the 2 opposite functions. So this work is. Okay? Yeah, good question. So why I choose this one? Because after I choose this one, I can easily get a physical interpretation. Maybe you can have other choice, but you have to be careful with your interpretations. Yeah, this is the thing. So the physical work is the same. Yeah. Very good. So what I'm going to do, actually, you can see, I'm going to choose the following. So this is the four. I'm going to use this one, choosing zeta prime 0 pi u prime equal 1/2 h00 prime u prime. This actually give me, I have this operator function, I can always do it. But this is the derivative of this means that this d h at 0 d prime d prime. This actually similarly give me the function of u as an integral. I get maximum data constant. It's fine. So I'm going to choose this one. Then also the second point, I will choose this. Prime is again u prime is equal minus 2 h11 plus This prime, sorry, this actually is in the x prime coordinate. Huh? We have too many primes. So this actually 2 prime in. So this prime represents the relative one. This is actually part. Prime equal H02 prime U prime 3 prime U prime equal H0 3 prime U. So if I choose this one, I simply choose it. Then I have, then you can prove, then you use actually this. This is a T X Y Z the current, right? You will see this is 0, 0, 0, 0, 0, 0, 0, 0, 0, H2, 2, H2, 3, H2, 3. Because this is 3, 2, 2, 3 symmetric. And this actually minus H2. So I forget the number, can we call this, let's say, 17? Sorry about it. So let's call this 18. So I have actually 2 components. So means by this I ask the question, what about if I choose different? Choose different, you don't have different components. Well, the reason why I choose this one, because I can easily get the physical interpretation. So you can choose different, but then you have to be careful when you interpret the component. Right? Yeah.
One question. When we are actually observing,
Yeah, observing.
two components, right?
Well, yeah.
So, how, are we in the process of observing? Are we actually putting our setup such that these gauge conditions are actually satisfied?
Yeah, this actually, you see, we are using, mathematically use the gauge residue to fix all the gauges, like what we do actually. This E prime E the corresponding net all equal, but it's all in the potential. So while we are doing this, we are left normal gauge choice. Your current component fixed, right? So this component is what you are going to observe. You are asking, this is exactly what we are observing. That's actually observational question. So observational is very complex. Why? Because you can see we are observing, let's say, if we put a light on Earth. Light on Earth, remember, the vertical coordinates is connected with CMB. CMB define a perfect coordinate. What means CMB? When we consider the micro background radiation, this is actually electromagnetic waves. We want to say this is, in that coordinates, the CMB is the corresponding fluid is a common. That defines our very ideal observational current. But now you narrow down to our galaxy. Our galaxy is moving in terms of CMB. So we know, by observation, we know what's the relations. Now we know our Earth is moving relative to the Sun. Our solar system is moving relative to our galaxy. Because our galaxy in the center, we're in the 2/3 of the center, right? So you have to take all the effects into account when you do really observations. This is totally different thing. I'm doing here pure theoretical. So we just get rid of all of the given choice from x to x prime to x double prime. This is theoretical. Okay? So I didn't connect with real observations. Connect with real observations is more common. You need to, like what I said, take out all the effects into account. So the really ideal coordinate we'll define is where the CMB is on the rest. That's the universal coordinate.
So you are saying that this choice of these functions is not affecting the observer's dynamics?
No, this actually we're purely theoretical. We are not really connected with observers. Theoretically, we take off the gate already. So how you connect with observers, this is totally another different setting. That's like a relation between observers and theoretical. So here we just do all pure theoretical. Okay. So now to answer another question, this you can see, this is actually like a gate chart. If you really define the next thought we're going to consider, using geodesic deviations, that were independent of your counting charts. That's exactly giving you the precise physical. So that's why I think I like that part. So I just spent 4 years to, I was working with colliding waves. So in order to see, I found there's actually, electromagnetic wave, we have further rotation, but Maxwell equation is linear. So that when you see, I have electromagnetic wave pass through a medium, let's say like water, then you have interaction because social term interact with the electromagnetic waves. Then it changes the direction. But if you just simply two electromagnetic waves, there's no interaction, no charge. So they just simply pass through. What about the gravitational waves? Gravitational waves, each one has a mass. So the Einstein equation is non-linear. So they were when they pass each other. So this guy serves like a solstice because the gravitational wave has an energy equal mass. Mass actually interact with the energy. So that's like this wave will serve like a medium. This wave will actually the polarization will change. This is a physical model. Now the question is how do you define polarization? This is actually a strong field. Why not doing linear polarization? Okay? So that's actually most of them be okay. I'm going to consider geodesic deviations. This is actually even for the weaker field, you can do the same thing. Here we should do it from the measure point. Why? Because it's simple. You can do the same thing using linear perturbation like what we are going to introduce next class, geodesic deviation. This is a rare definition. So then you just say, okay, I define this one. Then the title like what it says, not actually power return. In your time series, X y is a power return. So you have to consider this one. So that's why actually, this is spelling me actually about wine, more than wine. Interesting. How, okay. So then I say, okay, let's first choose the perfect. Once I choose any texture, that one is not a perfect, but if I can make a rotation, then perfect, then there are the angles. So I first define the angles of polarization in terms of not a perfect, then define the angle in terms of perfect. That angle actually gives you physically, because your current is perfect. It's unique, right? So that's okay. So this one here, this is just from measure component to give us directly intuition how things work. Real definition is geodesic deviation. That's why from very beginning this course, I emphasize a lot geodesic deviation. So in textbook, geodesic deviation is not so important. Why I emphasize it here? Because we use this to define polarization of gravitational waves. Okay, so let's see. Once we have this one, you can see we have this only components, then we have this one. Now I can write the measure. now we get everything in x double prime, right? I'm going to get rid of the x double prime. I just simply replace x double prime. Actually, let's do this double prime x. But you gotta remember, this is we're really working in this double prime. So then you can say ds squared equal dt squared minus dx squared minus dy squared minus dz squared. This is the background, right? The linear perturbation, because this is sort of dx squared. ds squared equal g equal h of eta ab plus epsilon h ab t x a t x b. So I simply drop the hollow term. Then plus this is h22 plus epsilon h22 dy squared, right? So it's h2, so plus 2 times epsilon h2 through dy dz. Then h through minus epsilon h2 to dy dz squared. Right? So this is our measure for the European wave propagating on x direction. Now our idea is to study the physics meaning of h2 to h2, right? So this actually, remember general relativity, the freedom to actually make a prime equal actually can be any of x, right? But the good choice means actually, in principle, GR, you can go to any coordinate, right? It can be any function. But now we want to say, okay, we have microscope. You cannot really make a dramatic change. If you make a dramatic change, we can immediately know this is actually artificial. What's happening if our actually almost equal, let's say because here, but I can make a small coordinate changes so that I can, these guys will introduce some artificial GAB. So that's why when we calculate this GAB here, there are 2 parts. Due to the corners and another part is due to physics. We needed to actually get rid of the corner part. So this is actually the case. So if we do this, then you will see now our HAB will now equal HAB minus 2 times ZAB, right? That's all. So this actually, sorry, I also want to write this like 5AB equal HAB minus 1/2 equals ABH, right? So this actually we have this. So when we do this actually, we have this 4 arbitrary functions. Then we say, okay, now I'm going to choose these guys. So this A equal 5A, 5B, right? Let me make sure the gauge transformation is correct. Yeah. So this, if I choose this one, now I get this like 5 A prime B A equals 0. Right. So you say, why I do this? Because if I do this, I'm working on the G prime coordinates as G prime, 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 often prime. So then if I choose this guy equals 0, right? This is like a commute. This guy is equals 0. So this is also 0. I'm left only 1 term. So this is the best choice. That's why we do this. If I do this, I get GAB prime equal exactly minus 1/2 epsilon 5. That's prime. So I get this one, so I'm going to write here. So making coordinate transformation is prime A equals x A plus epsilon theta A plus pi over. Then I choose this. This guys cannot be any now because the arbitrary can always fix the gate. So this B. So if I do this, actually I get 5 prime A B equals 0. Then my G A B prime equal minus 1/2 epsilon prime 5. This actually the first gate choice. Right? This actually our A step. Now we also show this is not good enough. We still have a gate choice freedom if I make the following double A prime equals prime A plus Z epsilon hat Z. Now, actually, this guy is prime like that equals 0. Or you can load this prime hat A equals 0. Actually, this condition is still certified. I still have actually double prime A B A equals 0. But I have one for arbitrary function. Not arbitrary, but just certify this equation. That's enough. Okay? So in this coordinate, I can have G prime A B equal minus 1/2 epsilon prime prime. I have the same thing here. This is my equations. Let's see. A, B, C, D. Okay? So you see now, I start from X coordinate. I get this one. Consider gate. Give me this one. I can use the differential equation theorem to get this far. This is always. Now, this actually leads to, in the H parameter, this equals 0. This is simplify my GAB to my, this is only this term. But I still have gate ready, which means this cannot completely fix my gate. I can still make similar transformation, but now that hat A certifies this actually wave equation socialized. You can consider it very soft. This socialized. Inhomogeneous, homogeneous. No problem, right? So then I can still have actually this is the same gate with the same form and GAB is the same. But the problem is that phi AB double prime phi prime AB they describe the same things feels like psi AB. Right? So sometimes I call phi AB sometimes psi. So this will be in Greek I call phi. This will be psi. So then actually we will work on this. I'm going to write here, X2 equals dt squared minus dy squared minus dz squared minus dx squared plus epsilon X22 dy squared plus 2 X2 dy dz squared minus so this is our measurement. So what I'm going to actually do the following, because the linear, I first consider H23 equals 0. It's independent two components. I just consider the physical interpretation of H optional. In this case, I have actually the space-time. I have dx squared x squared equals dt squared minus dy squared minus, let's put a dx squared in front, minus dy squared d squared plus epsilon. Well, I just like to put x together. You see, minus 1 minus epsilon h22 dy squared, right? It's minus. Minus 1 plus epsilon h22 dz squared, right? So this is actually my measure for when h23 equals 0. I want to be in presence. Okay? Then you see here. So if I consider, let's say, like what I said, this is actually my axis. This, let's see, I want to make sure it's simple. This is my y-axis, this is z-axis, right? So let's see, this is our x direction, the floor is yz. And now if I cut around the floor to one circle, I need to try to write look like circle. This is actually a circle, my circle narrow circle, right? So this is circle before the gravitational comes. When the gravitational comes, so let's say this guy is, suppose let's say t equal 0 case, this is positive, right? What's this? This is proper distance on the y direction, right? Remember now we narrowed down our x, y that cannot change. The x, y that is fixed. So that means actually if this is actually positive, now this direction, y minus is small quantity, the proper distance becomes smaller. So I'm actually, this is actually y direction. This will squeeze it, something like this, smaller, right? The proper distance. Proper distance is t equals 0, yx equals 0, z equals 0. This is the proper distance. Ly equal 1 minus h2. This is the proper distance, right? If you want, I can start what? Let's say delta y equal 1. The proper distance becomes smaller. But here become lighter, right? So this angle will make the distance larger. So what I observe is I will get something like ellipse so along this direction, right? So let's see later, suppose this oscillating later becomes negative, then it's always cross, right? So always either the axis, this will become longer or this will become round. But this is always the ellipse, the long distance either along the direction or y direction. So that's exactly what we call the plus paralysis. Okay? So you put actually, like what I said, circle there, then there are no gravitational waves. I keep shooting my lasers bounce back and forth. There are no phase difference. So in my screen, I cannot see any difference. So it's always the same waves oscillating. But once I actually, the gravitational pass through, you can see, normally I have same wave, right? Suddenly pass through, I get I know this, the gravitational waves pass through. Why I know the gravitational wave pass through, like what I said, if electromagnetic wave pass through, actually from this circle, it's always make the circle uniformly contracting. So, because electromagnetic wave has energy is always positive, converting to make it this is actually the test particle of the circle, right? Like the test particle moving in this direction, you flat this actual circle will remain the same. But once you are in the energy, according to Hawking-Pinus theorem, this actual conversion will become smaller. But for electromagnetic wave, this is always positive energy. Corresponding to our R component always positive. Later you will see this is 500 while I use the Newman parameter. So this always makes it smaller. But only gravitational wave. Stretch one arm, squeeze another one. So then I get something. So other others I cannot see the difference. That's actually the unique feature. That's why we just put the two arms. So you can put the two arms, you can imagine you can put it separate, right? So the now why Lisa put a three of them? Lisa actually has a three, right? So here only actually, in Lago only two, or seven, because this is not for us. Why Lisa put a three? Because this is for equal actually two parents arms. They equal two Lagos. Why we have Lago India, Lago? Because we want to have different directions. This is actually India's ideal place to put another Lago. So you can see easily polarization. For example, in the US, I put this one. In the India, I put this one. So like more like a circle. So if I put actually in principle, the gravitational wave has maximum 6 polarizations. Einstein is 4. You can say most general 0 is 6. So if I have 6 Lagos in different places, I can measure precisely the polarization. Then I can test 0. Einstein only 2. If I can observe more than 2, Einstein 0 is not correct. We need to multiply. That's why next generation is so important. So why we have been pushing to build more detector, because we want to get the polarization, to measure polarization. So the next generation actually of detectors, mainly one of them is a major polarization. Like what I said, why so important? Different theory has different polarization. Einstein is a theory predicted 5 polarizations independent. Brans-Dickinson theory actually has 3. Has 3 because you have scalar moves. This is called Brice move. You can actually, GR has 2 plus scalar 3 moves. So different theory have different polarizations. If I can measure how many polarizations the gravitational has, then I can test the theory. So that's actually important. Another important theory is a nonlinear effect called memory effect. Memory effect is nonlinear. So memory effect, this is 2 arms. We think gravitational will pass through. It's just something like this, they will return. But nonlinear effect find, no, they will not return. The distance will slither forever. So this is actually nonlinear effect called memory effect. This is another goal to measure for the measurement of gravitational waves. Okay? So this actually you can see this plus 2 actually we call cross components. This is just simply if I put it here, this the ellipse, the long axis is always either along y direction or z direction. Any other questions? Okay, now I'm going to this actually the H22 component. Let's come to the H23 component. The 2-3 components. Now let's see H23 different from 0, but H22 equal. Later you can put them together. in this case, dx squared is equal dt squared minus dx. Plus 2x. This is very simple, right? So what I'm going to do actually, I'm going to, this is my, this y. I'm going to rotate it 45 degrees. Y prime, z prime, this is exactly 45 degrees. Okay? If I do this, which means I'm going to let's use actually hat. So this actually, if I do y hat equal minus y plus z bar equal minus 2. I use actually z equal y. Either way is okay. In my notes, it's open. So it's just okay. Next, I think prime y2 equal minus h prime 02 h1 prime equal minus h2 third h01 prime equal minus 1/2 h0 plus h11 prime h23 prime equal minus h22. So this actually the four equations, the four constraints allow me to write this four components h1, 2, 1, 3, 0, 1, 3 in terms of the rest. Okay? So what we did is the following. We solved the Einstein vacuum equation in h prime coordinates. Then we get waves propagating along x direction, right? So we have, in principle, we have 10 components because the HAB, the symmetric, is supposed to be 16. But 16 because the symmetric, 16 minus 6, actually, you can figure out the 10 components. 10 components, now I'm using my Giza residues. I have, remember, corner transformation XI. Using that one, I find that this actually comes from prime A, B, A equals 0. I find the four components can be read in terms of the other 6, right? So from 10, I reduce 6, right? But we know gravitational waves have only 2 independent components. This is a very important point. Lots of time in university, people ask you, I have a 4 arbitrary functions, right? Corner transformation. So HAB has 10 components. What do you mean you have only 2 components? Where are the 4? 1. So this is exactly good. So after this class, I would like you, if somebody asks you, you can really explain to them, we have indeed 2 components. Because other 4 Giza residues. You see here, this is actually not so easy to understand. In principle, I have only 4 arbitrary functions. Each one related to the corner transformation x0, x1, x2, x3, right? So HAB has 10 components. How can you reduce 10 from actually to 2 by only 4 arbitrary functions? But we have Giza residues. That's actually fast. So this actually, from 10 to 6, now I'm going to use in this get ready to use, make another transformation. But remember, this guy is equal to 0. This cannot be, and this certify this one. That's fine. You see, certify this one. Remember, we consider plane gravitational waves along x direction. I simply actually assume my x a equal x a u prime, right? Because this is a wave. Then you can see this is certified the calculation. This is because this actually equal what? D squared psi hat a du prime dy prime equals 0, right? This is the same equation. This actually in terms of x, t prime x prime in terms of u prime y prime. If my psi hat is function of u, dy prime d psi hat equals 0. So this is indeed a solution, right? But this tells us this guy is the arbitrary function of u prime, right? So we have to do this step by step, 100% physics. Mathematically, you cannot make any perturbation approximation. What we really make approximation is epsilon. But here is the regular physics, mathematics, right? So this actually needed this, the solution of this is the get the residue z hat a. I'm going to use this full arbitrary function, which is a function of u prime only. But this get the residues, although not actually as general as z hat a, this is enough for me to kill fault. Why? They are function of the only u prime too, right? So here is the u prime, now here is also u prime. This allow me, this arbitrary function u prime, you can immediately say, allow me to kill 4 of this actually, 6. So that's why I'm going to reduce it to 2. Any question about this part? So I would like you guys to see the logic. So we are doing some, although we are doing some approximation, we are doing approximation some epsilon. But the mathematics is regular. Regular, I mean, thinking this actually is a function of this. I did not make any approximation why I eliminated the components. This is 100% precise, right? So if I do this,
Professor?
yep.
So there are only 6 physical parameters, or among 10 there are only 6, and these are for some gauge choices which you put on.
Yeah, this I can remember when we come down to x prime closure, right? We still have this gate residue, which means that if I make a corner from further corner from this one, my phi prime set over to this phi prime will describe the same gravitational field as this guy. There is no difference. So remember when we consider GIAN, electromagnetic waves, if we use, let's say, A mu and A mu prime equal A mu plus D mu lambda, this guy's E equal E prime, right? The magnetic field will be the same if you use, use this one. This actually is the corresponding magnetic field. Let's see, I'm using super vector. This super vector. They are actually equal. There is no difference. And also the B field. Equal B. So the same idea. So this guys, this is the potential. But the magnetic gravitational waves will be the same using this one and this one. Of course, also the same with phi AB, right? So this is actually third. They describe the same gravitational field. The only difference, when I talk about this one, this case has no gauge residues. I just take everything due to the artificial corner transmission away. Now, from here to here, we just take a part of them away. But we still have this gauge residues. We needed to take this part also away. After we take all of them away, the rest here, this is the physics. This is the gravitational waves. We are really want to measure. This is the wave part of our given measure. Okay? Any other questions? So I do not want to rush this part. Because the perturbations you see here, this is for gravitational waves. When you started black hole perturbations, our actually you work on this. So you will find it equal. You need to take all the gauge residues. Otherwise, when you talk about pathological model, things, that pathological model can be artificial from the cosmic perturbation, right? So when you consider from the cosmologies, our universe, the principles, homogeneous autotropy, I think you asked me later on, I will answer. So the homogeneous autotropy, this is the first approximation. Our universe is not homogeneous autotropy. We see the galaxy. We see actually a lot of structure. But the good thing is, this can be just simple linear perturbation. If a linear perturbation is sufficient to explain our whole universe. At the very beginning, when I was studying cosmology, I didn't believe this. This so complex universe. You can use homogeneous universe as the first zero-order approximation, then consider all the galaxies, a lot of structure, formed by a linear perturbation. This is a very broad assumption, but so far still works well. Okay? So this accuracy, what about here? The same thing. Okay? So now I'm going to use the gauge residues actually to narrow it down further. They're all in two independent compounds. Now, F2, H02 prime, 1, H12 prime equals F3, F3 prime, 1, 3, F12. So this actually I have a full integration. So where actually you can see, in principle, F equals F with 0, the partial reverse. But that cannot, this is most general. This should be actually equal constant. Can you see y equal constant? Or maximum depend on? I think it should be constant. You say why? Because remember, this guy is only a function of u, right? This is our beginning. So how they can actually, if each of them function of u, we cannot get this way. So in any case, even it's a constant, we say y r go to infinity, we do not have gravitational wave, right? Remember, we consider finite sources. In the infinity, all of them equal 0. So if we consider infinity, all of them 0, this constant has to be 0, right? So this actually, this is the general case, but if r goes to infinity, which we say we are infinity far from the sources, then h prime a b go to 0, which actually lead us f a equals 0. So I get actually simply put it in 0, 0, 0. This 0. Right? Yeah.
We take approximation that we are taking. For that, we do not consider R tending to infinity. We consider R to be large, but not infinity.
Yeah, you can consider it too large, but for example, this actually, if I have the sources here binary, so I'm actually here, but if I extend the gravitational waves, go to infinity, this definitely will be zero. I'm only in the, not infinity, but I'm in the middle. But the gravitational wave will continue, right? Will continue until 1, until near the boundary, in principle, right? But if I really go to infinity, this guy is supposed to be zero because, you know, it's 1 over r unless decay, right? So that's why, if I take that limit, this f I take. So this is actually the case. You see, if I equal 0, I can find my, let's see, I can find my 0, 0, and remember here, x prime equal eta ab h prime ab. This actually equal h prime 0, 0 minus h prime 1, 1 minus h prime 2, 2 minus h prime 3, 3. Right? This is our definition. So you just actually write this 4 equation, so 1. So I should actually, I'm able to express 4 of the components in terms of the others, because I have 4 equations, right? So by doing this, what I'm going to actually write it down. Here I will write the vacuum case, exactly what is the vacuum. You see now, if I consider vacuum case, this actually is, we have, let's say, a source here, let's say, binary black holes, emitting gravitational waves. We are here, we are far from source. So if we are in this region, our TAB equals 0. So I simply have actually GAB equals 0. If I have this one, I have this I'm first to work out this.
So you're saying that at the field point,
Uh-huh.
TAB is 0.
Yeah.
But yesterday you said that this TAB is for the source point.
Yeah, we can use the integration, the integrals connect this one with this one. Yeah, this actually, do you have the classical, Lambda Lipschitz paper, classical one? You can, let's say, I'm going to, first, now I consider here. I'm going to consider here. Then my field, I will use, let's say, okay, let's, this is actually the equation, right? I can actually, let me think about this. I can use growing function method. So I consider phi AB, let's see, this is called GAB delta function. Some, let's see, I have the wave here. This is actually x. This will be x a minus x. I'm thinking how to write this direct function. This actually, this prime x. So this direct function plus some, this I'm going to give z, because this is times of 0. So this actually you can consider constant. Using construct growing function, this actually point source. So I can write my phi AB, phi prime AB in terms of growing function TAB and G. This should be non-linear. That's why I get some confusion. X prime I D for X prime minus G. Minus D here we have weak field. You can see. So I use the growing function to write something. So here should be actually minus R. Should be minus 2, right? Just a drops that you can put it epsilon. So I use this one. You see now I connect this actually TAB. I connect the TAB with the source term. Then I can use some kind of approximations. consider this is 5 from here. So let's say I'm here. I can connect sources. I integrate it all. Then this one will match with what I get here. Okay? Yeah. So if you want to see clearly, there's a textbook called Landau. Underneath here. This is still probably the best textbook to find out this part. This is like a standard. This is exactly like what we did in electromagnetic waves. We just introduced Gravitational.
So which volume? This
I'm
book
sorry?
has 5. This book has a lot of volumes.
This cycle is called classical field theory.
Second one.
Second one, okay. Classical field theory. I forget the one. Yes. Okay. So, yeah.
Still in the equation, the Einstein's equation, which we were written before, in that we had written TAB. So that was for the source point, and then we do a Green function transformation, and then we get the TAB at the field point. Or is it the other way around? In the Einstein field equation.
So we have, let's see, I have Einstein equation. This is going to be TAB equal kappa TAB. Let's assume this is a gravitational wave, right? This is produced by, let's say,
This TAB.
yeah, this is TAB. This is TAB which produces the, let's say, binary,
Yes.
two binary black holes, produce gravitational waves. So I can use Gaussian function. There are many ways. This is actually one way Gaussian function, because this actually, then once you get this one, you can write this because of Gaussian function. So I can actually use the Gaussian function to solve this equation. My GAB will write like this. Right? So now I know the sources. Let's say this is like two binary black holes. The binary black hole, what do you do? This is actually H of the point sources. Right? You have, let's say, now my TAB equal, let's say, M1 delta, this is, I call it delta 1. This is trajectory. Okay? So I have plus M2 delta 2. This is actually trajectory of this single black hole. Then you plug your E integral.
So in between we are skipping this step, and we are putting TAB directly equal to 0. Because we cannot do
Yeah, we are putting, because this is actually what this is the integration you see from the source term, right?
Yes.
But I'm observing on the x term. So that's exactly Gaussian function. Gaussian function connect my sources x prime with where I'm observing. Okay? Even I'm here, I can integrate this one. Once I get this expression, I begin to mask this one with what I'm beginning to get. Then I can solve it. Okay? Do you have any question? E prime equals 0. Okay? Now, remember it's actually prime AB equal A prime AB minus 1/2 eta AB H prime, right? So if on both sides I'm going to eta AB, this will be eta AB. This is the first one, is H prime, right? Minus eta AB give me 4, but the minus half minus 2H prime. So this is I'm actually trying to get this one. So this actually tells us, now you see, when I want to say this HAB, so I have actually, now I'm going to get a, right? This have a AB, when I get a in, I have a H prime. Prime equal prime minus equal 0, right? So I get H prime prime equals 0. And if this is the case, prime phi AB equals H AB prime minus half E AB prime is equal to 0. So this is 2 to the 6, right? So I get this equation. Let's call this equation 2, this equation 1. So answer you guys one by one. We will do this equation. In the lecture, I call it lecture 10. So this is standard gravitational waves. So this is ion. The source term with observation. You need to do the matching. So what you do actually, using Green function, you see here x prime x. I'm integrating the source term. Here is x prime, right? But I'm actually observing here, xi. So the Green function actually connect these two, right? So this actually will I get from equation. But on the other hand, if I forget a source, I can solve the equation. Y can get a phi b. But I needed to match these two together. I will not do the matching because you can find this actually in standard book, lambdas. This is exactly like if you have a question, understand, look for electromagnetic field. When we have a charge, remember? In electromagnetic dynamics, you have a charge because there are also relativism and also background Minkowski space. Here exactly Minkowski space. What you just do exactly the same. Because space, you see actually this relativistic effect. You take this R out. Okay? There's 2 R's here. I'm integrating this actually. Let's see. This is my, oh sorry. This is R prime. What's that? Now this actually my R. So I have actually difference. This is what we call R. But if this actually much greater than this one, you can simply replace this together. Take this out, they all need it. This is the only thing. Because remember when I can see lean out this actual surface. If you want to consider how, then you go from. Okay? It's okay? Yeah. Okay. Thank you. So this actually the sense if you want to connect with the source. So I will erase here, then simply consider so just let's review what we did last yesterday. We assumed that the GAB actually can write this like HAB this order. 2 and GAB equals eta AB minus HAB plus. So this actually our first equation, so they actually satisfies GAB, GAC equals CB. Why I emphasize this one? This is a definition. Once you give me GAB, I can uniquely determine my GAB up, right? So if I know this one is not independent. This certify this relations. This is a reverse definition. So now actually after actually we arrive at the following conclusions. I'm going to write down the expression. So after all the calculations, finally we arrive at GAB equal 1/2 epsilon phi CA BC plus phi CB AC minus delta phi AB minus epsilon AB phi CB plus second order. Right? So since we linearize this actually, we just keep first everything. Higher order we just throw away. So do we have more chart? Oh, okay, I have. Once it passes this actual will squeeze it this direction, stress this. Then you see what's happening. If I keep shooting lasers, the laser come back here, also come back. But if the two arms has different lengths, then they have phase difference. What's happening? One phase difference is because when I'm shooting the laser, they have same phase. But when they come back, they have different phase. This actually, you all know, it's called interference, right? So once they superposition again, then you get actually different phase because then there's the interaction. Sometimes no shadow, sometimes amplitude. But okay.
We have.
Yeah, okay.
Now we can
Thank
start. Up, chalu kar de.
you. Okay. Yeah.
Okay, thank you.
Yeah. Question. I'm going to consider partial case. Remember, we consider plane wave. Plane wave means actually let's consider phi AB only depend on T and X. So sometimes I call it depend on TZ or not. You can, I think you might know that right as TX. So if we consider H is prime AB in function of AB prime only TX, then what happens is actually prime H prime AB will be equal dt squared d squared dt squared because this actually the because case, right? I'll put a c equal 1. Let's say velocity c equal 1 minus d squared dx squared h. This is going to be prime h prime a b t prime h prime. This equals 0. Right? This equals 0. Then you can see I have a unique function a b equals h. I call A prime T minus H prime plus H prime 0 B T prime H. This is one way. This is actually the wheel moving on positive x direction. This is negative x direction. This is plane wave, right? So this is a linear case. I can simply let's consider this guy equals 0. This one to be more specific. Because these two waves, one is moving this diagram is moving this direction, this is moving this direction. So I'm going to simply consider this wave, single wave. So let's consider only H prime A B equal H prime A B T prime minus. This will be equal to this. Sure. So you can actually consider this one too, or you can consider both of them. But remember, we are considering linear, there is no interaction between them. So you do not have this actual modifiers. So linear, you can always put them actually separately. So that's why, since they are independent, I'm going to consider only one. Wow. Now, this is actually the plane waves, right? I'm going to use this again. Because that's a way, but I'm not using my gauge choice here. Right? This has to simplify this. So I needed to consider the gauge. So consider the gauge choice. I'm going to this like a t prime plus x prime v prime equal. This is the definition. T prime. Oh, let's just use. This is u prime minus this one and plus x prime. So instead for using tx prime, t prime x prime, I'm using v prime. V prime, u prime. This is two independent corners too, right? Why I use this one? Because in this case, then we have actually h prime a b t prime minus x prime all big. This is actually u prime, right? So instead of partial derivative, I'm going to consider only one argument, right? So if we do this, then you can say for any given function, df dt prime will equal d u prime dt prime. If this guy is only a function of a u prime, this is exactly the case, right? dt prime d, now this will be f prime. F prime is the word for u prime. Plus dv prime dt prime df dv. So this equals 0 because f is a function of only u prime. Now u prime and v prime are independent, right? So this equals 0. This equals 0. I have du prime dt prime du prime 1. So this is f prime, right? So you can do the same thing actually. df u prime dx prime will equal du prime dx prime f prime plus dv prime dx prime df dv prime. Like what I said, this guy is equal to 0. I simply equal this like a du prime dx prime minus, right? So I just actually write the partial derivative was sort of t prime x prime in terms of the ODE. This is actually simple. Here's my function. This actually only depends on t prime minus u prime. So we just simply use this. Then you can actually, now I'm going to consider, you see, we have a dx prime a h a e prime minus 1/2 delta a b h prime. This actually equals 0, right? This is our gauge choice. Now I'm going to actually consider, let's say, first b equal t. Then you can b equal x, b equal y, b equal 0. So after I consider this, I will not go to the details, just plug this in, right? So then we can actually can easily find there's all 4 equations. We're giving d, so d u prime h 0 0 prime plus h 1 0 1 minus 1/2 h prime equals 0. The same for my equation. Du prime h 0 1 prime h 1 1 plus 1/2 h prime equals 0. prime, H02 prime, plus H12 prime equals 0. Prime, H02 prime, H13 prime. So this anchor equates to, let's see, I call equates 5. So I get that this anchor, my Lorentz gate or Einstein gate, whenever we call, sometimes we call it Newtonian gate. So this is a partial derivative I can integrate it, right? When I integrate this, you will see this guy will be, for example, this, the first one. This is again like F1.